Hi there, I'm Martha Gross, and I'm delighted to welcome you to the WTS annual conference tour of the Hampton Roads Bridge Tunnel Expansion Project. As the technical director for Tunnel and Islands for this project, we'll be taking an overview today to look through Virginia's largest infrastructure project ever. We'll learn a little bit about how the project came to be, how it helps solve some of the congestion challenges in the region, and how it will be the VDOT's first bored tunnel ever. We'll hear from stakeholders, look at some of the technical challenges that go into solving this project, and see renderings of what this project will look like at its planned completion in late 2025. Join us for the adventure. Let's take a look at Hampton Roads on a map. First of all, the name of the region actually stands for the maritime roadstead, or the confluence of the waterways in the southeastern corner of Virginia. This was significant in shaping the history of this portion of the state, and has also given us many water crossings as motorists and travelers to need to get from parts of Hampton Roads across this waterway, between the city of Norfolk in the south and Hampton in the north. Sometimes the question is raised why we have so many tunnels here in Hampton Roads instead of big signature bridges across the harbor. The reason has to do with the Navy, because Hampton Roads is home to the world's largest naval installation. Originally, people were able to cross this waterway by using ferries for decades, but as the population increased in Hampton Roads, it became clear that ferries were not a long-term solution. So, in the 1950s, the Virginia Department of Transportation looked at how do we make a fixed crossing, how do we make a permanent tunnel across this waterway. Thus, the Hampton Roads Bridge Tunnel was born. In 1957, the first crossing was opened. It was an engineering marvel of its time. In fact, it was the first tunnel anywhere in the world to be constructed between two artificial islands. This unusual approach for the time was necessary because of the tunnel technology of the day that limited the ventilation. So, as the population of the region continued to increase, a second tunnel was built in 1976, expanding the crossing to 4 lanes total between the cities of Norfolk and Hampton. However, since 1976, the amount of capacity of this crossing has stayed the same, and congestion has only increased since then. Every region has a traffic choke point that it loves to hate. Well, the Hampton Roads Bridge Tunnel is that choke point here in our region. Every day, traffic backups extend several miles in each direction, and during peak summer travel, when traffic is over 100,000 vehicles per day, the Virginia Department of Transportation looked at alternatives for expanding capacity across the water. But as VDOT looked at alternatives for managing the congestion, it was realized that it wasn't just necessary, it wasn't just sufficient to widen the crossing across the water, but rather a more regional solution would be needed in which a longer stretch of Interstate 64 was addressed. Here in this fly-through, we start in the city of Norfolk, and as we come north or westbound on I-64, we see the 2 lanes in each direction that we widen to a total of 3 lanes in each direction, or 6 lanes, full-time lanes total, to be able to address the additional capacity needs. In addition to the 6 full-time lanes, an additional shoulder lane for peak travel periods was also proposed. As we continue across the water, we reach the city of Hampton and conclude the project at the Settlers Landing interchange, showing about 10 miles of total interstate corridor that would be addressed by the Hampton Roads Bridge Tunnel Expansion Project. But I'm getting ahead of myself, because how was this alternative selected? There was tremendous public outreach throughout the cities of Norfolk, Hampton, and the surrounding community to understand what would best fit residents' needs and address community members' concerns. There was outreach also to the military, to industrial partners, to the cities and other members of the region to ensure that the project solution addressed the region's true needs. As with many major projects, one of the challenges with enabling a solution like this to occur was the price tag. Early estimates indicated the project would cost several $billions. As we'll hear shortly from HRTAC Executive Director Kevin Page, the region was able to come up with unprecedented cooperation to enable a funding solution to be established.
The turning point to me for the Hampton Roads Bridge Tunnel was the coming of the Hampton Roads Transportation Fund and the Hampton Roads Transportation Accountability Commission. HRTAC has been a real game changer for the Hampton Roads region, where we saw 14 jurisdictions and 5 elected legislators come together in a very courageous way and work as a team to provide for the economic vitality and quality of life, not only for our current generation, but future generations to come.
Once the project funding was in place, VDOT began the procurement process in 2017 and 2018 to find a design-build partner to construct this project. The contract was awarded in April 2019 as the largest single infrastructure project in Virginia's history.
Welcome to another glorious day in Hampton Roads. We are pleased to be here and to make this official, our plans for funding and delivering the new tunnel.
This project will add 2 new 2-lane tunnels. It will widen the 4-lane sections of Interstate 64 in Hampton between Settlers Landing Road and the Phoebus Shoreline, as well as the 4-lane section of I-64 in Norfolk between the Willoughby Shoreline and the I-564 interchange. These projects will help us continue to grow our economy and create access to opportunity for not only Hampton Roads residents, but all Virginians.
Today we are celebrating the construction and the launch of construction of a generational project that will increase capacity, reduce congestion, improve safety, support emergency evacuation readiness, enhance significantly our quality of life, and deliver the largest transportation asset in Virginia's history. A $3.8 billion investment.
To have the largest project in the nation right here in Hampton Roads. I mean, y'all did it. This is amazing.
The project began with a limited notice to proceed. This was done so that the key environmental permits could be acquired and proper protections for the environment assured as the design of the project was advanced and before full construction began. Notice to proceed was achieved in September 2020. Shortly after that, in October, a groundbreaking ceremony was held to mark the start of full construction on the project.
I am very privileged to be standing on this platform today with 4 others without whom we would not be here. Governor Northam, Mayor Tuck, Mayor Alexander, Mayor Johnson. Thank you all so much for being here. And I'm sure you know that we are here to recognize a significant milestone, the official groundbreaking of the $3.8 billion Hampton Roads Bridge Expansion Project, the largest single infrastructure construction project in the Commonwealth of Virginia.
What an exciting day. I don't know about you all, but I'm excited about today. And Pam and I, we raised our families like a lot of you all have in this area. And I know we've all spent many an hour sitting in traffic out here. And this is just such a big, big deal.
Here we'd like to feature our project partners for the Hampton Roads Bridge Tunnel Expansion Project. The selected design builder is a consortium of 4 major construction companies: Dragados USA, Flatiron Constructors, Vinci Construction Grand Projet, and Dodin Campanot Bernard. These 4 contractors are grouped together to construct the varied elements of scope for the project, ranging from highway widening, bridge expansion, marine bridge construction, island expansion, and of course the construction of the tunnel itself. For the engineering design of this complex project, the design joint venture of HDR Engineering and Mott MacDonald are supporting Hampton Roads connector partners for the joint venture. But of course, these are not the only partners helping deliver this signature project. Many other firms, hundreds and hundreds of other firms, are also participating in making this project a reality. We'd like to feature here some of the outreach to disadvantaged business enterprise and small women and minority-owned firms, or DBE and SWAM companies, who are playing a major part in making this project possible. The success of this effort has already paid off considerably. We see that the number of agreements with DBE and SWAM firms, as well as the total dollar value awarded, is already considerable, even as the project is only 2 years into its 6.5-year span. We'd also like to underscore here the additional opportunities available on the project. This job has an on-the-job training program with a total of 80 trainees whose skills will be supported and whose training will be advanced through this program to enable them to apply these skills on future projects in the region after this job is complete. One of the neat things about a virtual tour such as we're having today is the opportunity to see the renderings and animations of what the project will look like when it's complete. Here, we're coming from north to south through the 10-mile project corridor, starting the city of Hampton. There's about 1 mile of highway expansion or highway widening in the city of Hampton. We then reach the north shoreline, where we have approximately 3,000 feet of marine trestle bridge. Currently, there are 2 bridges with 2 lanes in each direction. At the end of the project, there will be 8 lanes of capacity between these 2 bridges, 6 full-time lanes, and 2 part-time shoulder lanes for periods of peak travel. As we reach the North Island, the 4 lanes of expanded capacity will then enter this portal, continue underwater through the new bored tunnels that will go underneath the Hampton Roads channel, and then come up on the South Island. Because the South Island was built larger in the 1970s, it currently is sufficient in size for the portal or the opening that will accommodate the new 4 lanes coming back up to surface on the South Island. We then have another 6,000 feet of low-level marine trestle bridge between the South Island and the Norfolk shoreline in the Willoughby area. As we reach Willoughby, we have some highway widening, as well as another mile of marine trestle bridge across the Willoughby Bay. We then continue southward into the city of Norfolk for the remainder of the project scope, which consists of highway and bridge widening down to the I-564 interchange. One of the challenges of giving tours of an underground construction project, such as the Hampton Roads Bridge Tunnel expansion, is the challenge of being able to see underground and see where that work is taking place, unlike a bridge or a highway portion of a project where the work is highly visible and able to be seen from the surface. So, in order to help us out with that, we've enlisted the aid of some 4D modeling, which is part of the project design for this undertaking. Now that we've had an overview of the entire project, let's zoom in and take a look at the South Island. This is where the one end of the tunnel will start. And here we see on the near side of the South Island some of the traffic shifts that will be in place to help this work happen. On the left-hand side of the picture, we see some of the water treatment plants and industrial facilities that will become part of the treatment of the materials coming out of the tunnel. On the near side of this view, we see the new dock that we built, as well as the conveyor pier on the far left that will carry the tunnel spoils for disposal. We're also seeing now the diaphragm walls or slurry walls that are being built underground around a tri-cell or 3-circle excavation or shaft, which will be where the tunnel starts. Toward the left-hand side, we see additional slurry walls or diaphragm walls. Speaking of excavation, let's take a closer look at what it means to dig a hole 65 to 70 feet deep, approximately the size of a football field, in an area below the groundwater table. Once the tri-cell shaft is built and the walls are constructed, excavation with heavy equipment will continue. Struts will be built across the shaft to hold it open, and then a base slab will be poured across the bottom to seal off groundwater, as well as to provide a firm surface to work on and for the TBM, the tunnel boring machine, to be installed. We see at the very left the head wall where the machine will cut through the wall to start its journey underwater toward the North Island. And then, after it reaches the North Island, the TBM will turn around, come back from the North Island to the south, and re-enter the South Island on that left-hand side of the shaft. I spoke a moment ago about the North Island expansion, but let's take a closer look at this operation. Not many projects, after all, have the opportunity to build an island as part of their scope. The way this is done is first a rock perimeter is built around the footprint of the new area. Although it may simply look like rocks, it's actually an engineered structure that is designed for the wind and wave loadings in this area in order to protect the sand of the island from storms throughout the project's 100-year design life. After the rock perimeter is built with smaller stone on the inside and larger armor stone or rock around the outside, designed for the size of the wave loadings in this area, the inside of this footprint is then filled with sand, which is vibrocompacted and brought up to an elevation of plus 11 or 12 feet to match the elevation of the existing island. This is where the shaft or pit for the tunnel boring machine will be constructed, into which the machine will come at the end of its journey from the South Island, turn around, and then continue its journey from north back to south for the other 2 lanes of the crossing. The South Island, however, had become home to colonies of nesting seabirds, which had made their home here over the past decades. So, as part of the project, the seabirds were encouraged to find a safer nesting ground for the duration of the project. Let's see a little bit more how that was done.
For decades, seabirds, and lots of them, occupied almost every inch of prime nesting territory at the South Island of the Hampton Roads Bridge Tunnel. But a nearly $4 billion expansion project at the HRBT necessitated efforts to coax the colonies from the island. That's where Rebecca Gibson, Zoe, Nike, and 18 other of Gibson's trained border collies come into the picture. They're part of the flyaway geese family, on assignment to work from sunup to sundown 7 days a week until September to keep the seabirds from nesting while work is underway on the expansion project. In March, Virginia's Secretary of Transportation Shannon Valentine, who oversees VDOT and its expansion project, traveled to the HRBT to observe the dogs at work and to also eye new nesting grounds for the birds at nearby historic Fort Wool, which is closed to the public. Secretary Valentine says through collaboration and cooperation between VDOT and the Department of Game and Inland Fisheries, DGIF, a plan to protect the birds took flight. Fort Wool was prepped to receive thousands of the feathery flocks. And to ensure ample nesting habitat, DGIF is also anchoring sand-covered barges between the fort and South Island as additional space for the birds. So far, man's best friend appears to be key to keeping birds away from the work zone. Meanwhile, a 24-hour around-the-clock bird monitoring program will be maintained throughout the life of the construction project, which is due to end in late 2025.
Now we're going to focus a little bit more on the tunnel part of the construction project. Here we're going to zoom in on the South Island and use our virtual tour superpowers to look underground. Those different colors we see are the different layers of soil that are part of the Hampton Roads geological strata. We see under the South Island there's a lot of soil variability, and as we look to the left we see the circles for the 2 new tunnels. On the right we see the shapes for the 2 existing tunnels. One difference between this project's technology and previous projects was that the 2 existing tunnels, those on the right-hand side, were built using the immersed tube tunnel construction methodology, in which a trench was dredged from the surface, tunnel segments were set into that trench, and then covered with sand and rock fill. On the left-hand side, though, the bored tunnel technology is being used, in which a tunnel boring machine is cutting those round circles as we go now from the South Island, arriving at the north. I mentioned earlier this was VDOT's first tunnel project constructed with a tunnel boring machine. To understand the scale of what this machine looks like, we've overlaid it here, or photoshopped it next to the project's co-located office building. The building is about 55 feet tall. The TBM, or tunnel boring machine, is 46 feet in diameter, so we can understand for scale how massive this machine is to create the new 2-lane tunnels. The machine is being custom fabricated in Germany by a company called Herrenknecht. Here we see a view of the Herrenknecht factory. The machine is being built in its outdoor yard, and we see some views here of the components of the machine taking shape, for both the interior parts, the excavation components as well. Let's now take a 3D fly-through looking at the full machine. This is the very front part of the TBM, the tunnel boring machine called the shield, which contains a lot of the excavation machinery. For scale, we see in green there some scale figures of the workers who will be working inside the TBM while it's in operation. The pressurized chamber that will allow workers to work under pressure when necessary in order to deal with the soft soils that the tunnel boring machine will be digging through, as well as the machinery and piping for excavating the soft material as it's dug out through the front of the machine. We're now inside the cutter head, looking out through the front of the machine, and then in this 3D animation, coming back and looking at it from the very outside, where we can see the different types of teeth and tools and cutting discs that will be part of cutting the soil as that 46-foot cutter head turns and advances itself forward through the soft soils that we saw in the previous underground animation. We're next going to take a tour through the remainder of the TBM that supports all the mechanical processes. This is starting at the very back of the TBM, keeping in mind the entire machine is over 400 feet long. This supporting machinery here is called the gantries, or the backup or trailing gear, and it carries the mechanical parts and industrial piping that carries not only the excavated material from the cutter head out to the back of the machine and ultimately through the tunnel up to the surface where the excavated material is treated for disposal, but we also see here the concrete segments right there in front of us that will form the permanent wall of the new tunnel. Those segments are bolted together. There will be 9 segments forming each ring. Each segment weighs about 10 tons, and it will be transported by a multi-service vehicle to the machine, then put on a conveyor, carried into the machine, and then ultimately each segment will be picked up by a vacuum erector and rotated into exactly the right place along the wall of the new tunnel. Once 9 segments are fully in place, that will form one ring. The TBM will then push itself off using thrust jacks from the completed ring to advance the machine forward to excavate the next portion of tunnel and then continue the process to erect new rings as it continues along. This now brings us to the front of the machine, matching up with the shield that we saw previously. Now we have a little treat for the mechanical and structural engineers in our tour group. We're going to take a closer look at how the TBM actually works and does its job underground. We see the cutter head that I mentioned in the previous animation doing its work, rotating at maybe 1 or 2 RPM, not very fast, but at this diameter it's certainly sufficient to cut away and carry away these excavated spoils we see here. We notice a screw conveyor that carries the soils up to the back of the machine, and then we also notice the segments that I spoke about earlier. Those segments are precast in a plant above ground, carried into the TBM, and then picked up one by one and rotated into place, just as we spoke of earlier. This shows the process with the thrust jacks, each one retracted and then pressed against the segments as they're installed to fit them firmly into place, as well as to provide a launching point for the TBM to push itself forward. In order to provide a 100-year design life for the tunnel, grout is pumped into the small space behind the back of these concrete segments and the soil to provide a permanent seal. As the machine advances forward, we will have approximately 7,900 rings consisting of 9 segments each for each of the 2 tunnels across the Hampton Roads channel. The process will take about roughly 1 year for the tunnel to be bored in each direction, so we look forward to having the second of these 2 tunnels complete in approximately 2024. But before a tunnel boring machine can start its work, it needs a name. And in order to name the HRBT tunnel boring machine, we turned to the school children of the Hampton Roads region. We reached out to middle schoolers for their ideas and creative submissions on what this machine should be named. By tradition, machines typically have female names, so we invited the school children to use their creativity and provide their suggestions for what the name of our machine should be.
And Noah. And we have your midday news here at the St. News Network. Our first segment is about a great project which will make the drivers in Hampton Roads very happy. Take it away, Alex.
Thanks, Maddie and Noah. It's another dicey day on the HRBT. Just look at that traffic and those angry drivers.
Get out of the way, easy driver. This is a tunnel, it's a road.
Good news is on the way. A new twin 2-lane tunnel will be built with the help of a TBM, or tunnel boring machine. For more on that, let's go to Nolan at the NASA Langley Research Facility in Hampton.
We are excited to share a possible new name for the tunnel boring machine. With me, I have a few NASA employees here to share with our viewers the extraordinary Mary Winston Jackson. Tell us who Mary Winston Jackson is.
Thanks. Mary Winston Jackson might be known to your viewers as one of the characters in the hit movie Hidden Figures.
Born on April 9th, 1921, right here in Hampton Roads.
Mary Winston Jackson graduated from the Hampton Institute with a degree of Math and Physical Science in 1942.
She was a teacher, but is best known for being an incredible engineer.
In fact, she was part of a special group of aeronautical engineers.
So, what does she have to do with the tunnel project?
We believe in order to really highlight this incredible woman's accomplishments and contributions to Hampton Roads, our nation, and our world, the tunnel boring machine should be named after her. Let's call the TBM the Mary.
Back to you in the studio. Mary Winston Jackson was certainly an incredible engineer and highly successful despite difficult times in our nation's history. Naming the TBM after her would be a great way to honor her. Let's do this!
The winning entry was Mary, named for Mary Jackson, the aerospace engineer from Hampton, Virginia, whose work was featured in the recent film Hidden Figures. This logo shown here will be on the side of the TBM, and the stars next to Mary's name denote Mary Jackson's work as an aerospace engineer, and the curve between the M and the Y denote the tunnel. Let's take a look when the winning team of school children found out that their entry had been selected as the winner.
You made it into the finalists. Actually, you are the first place winner. Okay, congratulations, huh? How about that? So you are the first place winner. First place winner, yes. So you won it. We had a lot of good names and we had a lot of great presentations. You guys just knocked it out of the park, I thought. So good job.
So now we have the part of the tour you've been waiting for, the actual current progress. So if we were out on the site today, we would have the opportunity to see some of the things you're about to see. But leading up to that, we have the benefit of some, maybe not quite time-lapse, but an opportunity to look first what we're seeing here, September 2020, looking at the progress of the South and North Island at that time. We'll then look ahead to December 2020, the progress that had been made at that point. And then we'll look at March 2021, moving ahead another 3 months to see how the progress is moving ahead rapidly. The things to pay attention to in these sequences of these three aerial videos is to look at the perimeter of the North Island. You'll see a lot of progress there as that rock wall, that rock armor stone is being built. And you'll note as the sequence of videos move forward how that island footprint, that rock perimeter wall, is expanding. That work is currently underway and sand fill has recently begun. The second thing to pay attention to in this sequence of videos is the South Island. In that open, what was originally the open area on the side of the South Island, how increasingly amounts of construction equipment are busy at work there. Initially, we see what are called hydromill trench cutters digging rectangular holes that go down to a depth of 190 feet. Those will be filled with concrete and will form the diaphragm walls or slurry walls that become the edge of that tri-cell launch shaft that we looked at earlier. Also in the South Island, you'll see additional construction operations underway, building the offshore pilings for the dock that will be used for deliveries of TBM pieces as well as the concrete segments. You'll also see offshore pilings for the conveyor that will carry the spoils offshore to barges for disposal. Other activities you'll see taking place on the South Island include the installation of slurry treatment plants to treat the slurry as it's used to build these underground walls and to recycle it for use in subsequent walls. You'll also see jet grouting operations and the initial parts of soil mixing operations, which are part of the ground improvements that will be used near the path of the tunnel to help treat the soft soils to prepare them for the tunnel's construction. Now that we've had the overview of these aerials, these videos, let's zoom in and take a close-up look of some of the things you might see if you were walking around the job site today. The project features a large amount of specialty construction equipment. One of the pieces we're especially proud of is the hydromill trench cutter. That's what we see here, and it's the digging tool that is used to excavate the slurry walls that are first filled with slurry to hold these deep holes open. Rebar cage is then inserted, and finally concrete is poured into these deep holes to form the permanent wall. In the next picture, we see what one of these reinforcing steel cages looks like. It looks big, but that's actually only half of a re-steel cage for one of these slurry walls. Because of their great height, they're built in two pieces and then spliced together partway through in order to cover the full depth of the reinforcement needed for each of these slurry walls. In the next picture, we take a close-up at the rock placement operations on the North Island. This is a clamshell that's carefully placing the stone, the engineered stone that we heard about earlier, in just the right place along that footprint in order to form the new perimeter for the North Island as it's expanded. In the next picture, we see a test pile operation. We talked a little while ago about the marine bridges that would be built as part of the project scope in order to make sure that each piling is strong enough to take the design loads that are intended for its long-term durability. A very heavy load is placed on top of a test pile in order to measure its performance and how it acts in the soils and with the pile driving characteristics that are planned for use on the project. Once a test pile operation is analyzed and deemed successful, then the remainder of the piles on the project are built using the information gathered from the test pile operation. Here we see the heavy load consisting in part of crane counterweights on top being used to test the pile that is underneath this frame. And finally, we see some of the landside work. Even though we focused primarily on the marine work for this tour, with the marine bridges, the island expansion, and the preparations for tunnel construction, we still do have miles of highway widening going on in the cities of Hampton and Norfolk. This shows some of the early work taking place currently in Norfolk, where pile driving is beginning for temporary trestles that will support cranes in their access to expand the bridges along I-64 in Norfolk. Now we've invited a virtual guest speaker to tell us a little bit more about the island construction progress. I'm happy to introduce Megan Pym, Hampton Roads Connector Partners project manager for the island expansion work, and she'll tell us, as shared in a recent podcast, a little bit more about how the North Island expansion comes to life.
My team and I were responsible for getting the North Island expanded and prepared for the future tunnel. So the current North Island is actually too small for the future tunnel footprint. We have to expand it by about 16 acres, so we'll build out to the west side of the existing island. So what we had to do first, we had to do some dredging to remove some clay pockets. And then we build out the bun, which is kind of like your core layer. And then on that, we place a different type of rock type. So there's 3 layers. Depending on where you are in the island, it dictates the rock type. So on the south end, where we have a lot of the wave and the current action, we have larger stone. And then as the island goes north, kind of towards the Hampton side, the rock size gets smaller. So those transitions are pretty tricky, and meeting all the layer tolerances are very complex. And then once we get the bund substantially built, we'll place fill. So we actually have 2 different types of fill as well. So the first type of fill we put into about +5, and we vibrocompact that. It's a very technical, it's not really done a lot here in the US. And then once the first layer of fill is, then we'll put the second layer of fill, and then we'll roller compact, and then everybody else can come build their parts.
As we conclude our tour, I also want to draw attention to the communications and outreach that we've used to keep the public and stakeholders informed about project progress. You heard Megan Pym earlier share a Tunnel Talk podcast that we periodically produce for the project. We also have monthly email updates, project newsletters, outreach to the public through virtual meetings, and other media. We invite you to visit our website at hrbtexpansion.org to sign up for the newsletter or to follow other parts of the project progress, or follow us on the social media linked there. Thank you for joining us for today's virtual tour of the Hampton Roads Bridge Tunnel Expansion Project as part of the WTS Annual Conference. We're excited to continue the work to deliver Virginia's largest highway infrastructure project, relieving this traffic choke point in order to support and further enhance the region's economy. We'll now have a question and answer session, and I look forward to taking any questions you may have about this project.